Session 7 is fairly short. We got 3 talks to go right before lunch. And the session 7 was originally going to be Richard Tanabe, but he was unable to make it, so I'm his poor stand-in. The session, Technological Advances in Deposition Measurements and Monitoring. And our first talk, I believe, is online. Dr. Wendell Waters from Brown University, and if you are ready to go, we are seeing your slides.
All right, great. All right, well, thank you for the introduction. Today I'll be talking about using nitrogen stable isotope technology to further our understanding of atmospheric nitrate deposition. This work will provide an update on nitrogen isotope values from CastNet samples in the northeastern United States, as well as highlight our advances in stable isotope technology in recent years. So first of all, I'd like to acknowledge my research team of undergraduate and graduate students, collaborators, and funding sources that made completing this research possible. So I want to start with the role that stable isotopes may play in informing our understanding of nitrate deposition. So as most of us here know, atmospheric nitrate derives from the precursor emissions of nitrogen oxides, which may originate from various sources that have both spatial and temporal variabilities. NOx is then oxidized in the atmosphere, leading to the formation of gaseous nitric acid, as well as particulate nitrate that may be transported several hundred kilometers downwind from the original NOx emission source. Both nitric acid and particulate nitrate can undergo dry and wet deposition, leading to environmental consequences such as eutrophication. Further, particulate nitrate represents an important component of fine particulate matter across the United States, with implications for air quality and climate. So over the past few decades, we have significantly reduced our nitrate-related deposition, but there's still more work that needs to be done. For example, recent work has highlighted that NOx emission reductions in the United States have begun to unexpectedly slow down. So thus having technologies that can be used for nitrate source apportionment would be really beneficial. That could provide a direct link between deposition and emission sources. And nitrogen stable isotopes had been previously suggested to potentially enable source apportionment, which will be the subject of my talk today. So not all of us here have a background in isotope geochemistry, so I'll highlight how stable isotopes can be used potentially as a fingerprinting tool. So stable isotopes fractionate in small, measurable, and predictable ways. We can think of these fractionations as a couple categories. For example, kinetic isotope effects, which really describes the relative rates that stable isotopes are reacting, or equilibrium isotope effects, in which isotopes may partition between different compounds that depend on the energetics of the system. So these isotope effects often lead to emission sources and sink processes to have characteristic isotope values or fingerprints that can potentially be tracked in the environment. So thus, isotopes can provide an additional dimension of trace gas and aerosols that can add importantly to our concentrations, our mixing ratios. Stable isotopes are quantified typically using delta notation, which expresses the ratio of the heavy isotope relative to the light isotope for a sample relative to an internationally recognized reference material, which for nitrogen is atmospheric air. And delta values essentially quantify the relative abundance of the heavy isotope, such that a higher delta value just means it's the greater abundance of the heavy isotope. In the case of nitrogen would be 15N. So in a previous landmark study, nitrogen isotopes were analyzed to investigate nitrate deposition from CastNet and NADP sites in the eastern, Midwestern US in the mid-2000s from a series of studies conducted by Emily Elliott, Carol Kendall and company. In this work, they found that the delta 15 values had significant seasonality, with typically high values observed during the winter and lower values observed during the summer, which were then suggested to be driven by the increased importance of coal combustion during colder periods. Indeed, they found these significant correlations with delta 15N and nearby stationary NOx emission sources near the various CastNet and NADP sites. So I think two major takeaways from this study were that the delta 15N values of nitrate may be a sensitive tracer of NOx emission sources, and that stationary NOx emission sources, primarily coal combustion, were the dominant contributor to nitrate deposition in the mid-2000s. So motivated by this study, in recent years, our community has significantly improved our understanding of the delta 15N emission source values of NOx, as well as our understanding of isotope effects associated with NOx oxidation. And then further, since the time of this study, across the United States, but particularly the northeastern United States, we've experienced a significant reduction in NOx emissions, such that we can evaluate how these reductions have impacted nitrate deposition, and we can use delta 15N as an important source apportionment pool. So over the past few years, we have significantly improved our understanding of NOx emission source delta 15 signatures. So utilizing the National Emission Inventory, we have modeled the expected delta 15N NOx emissions across the contiguous US, which are shown as an isoscape here on the right, which demonstrate there's a significant spatial temporal variability. I think overall, this isoscape showcases the potential to utilize delta 15N to connect NOx emissions to spatial temporal nitrate deposition trends. Of course, emissions aren't the only driver of these isotope values, and it's also important to consider the role that chemistry might play on fractionating delta 15N values as NOx is oxidized to nitric acid, such that the original delta 15N emission source signature may not necessarily be conserved in the atmospheric nitrate deposition process. This is because NOx is an extremely reactive gas that may form a variety of different oxidized forms of nitrogen that have different environmental fates as well as environmental lifetimes. And then this can lead to significant isotope effects. And we have recently developed a new chemical mechanism that explicitly incorporates the 15N isotope, such that we have a much better understanding of the major chemical processing and isotope effects that influence delta 15N as NOx is oxidized. So in this study, we provide an update on the delta 15N values of atmospheric nitrate in the northeastern US from 3 CastNet sites, including Abington, Connecticut, Connecticut Hill, New York, and Woodstock, New Hampshire. So for those unfamiliar, the CastNet program utilizes a 3-stage filter pack sampling system in which air first passes through a Teflon filter, which is used for the collection of particles such as particulate nitrate. Air then passes through a nylon filter for the collection of nitric acid. We acquired samples from the various study sites from a period that spanned December 2016 to December 2018, and these samples are collected at 1-week intervals. These samples were shipped to Brown University, where we remeasured the nitrite and nitrate concentrations to assess the stability of the sample extracts. We then conducted nitrogen isotope analysis of monthly volume-weighted samples using the well-established denitrifier method coupled to a isotope ratio mass spectrometer. And then we combined our concentration and our isotope data for further data analysis, including air mass back trajectory calculations, NOx emission modeling, as well as we compared our results to the 3D atmospheric chemistry and transport model, which we use GeosChem for this study. So this figure displays the delta 15N data that is sorted by site as well as forms of atmospheric nitrate, including nitric acid, particulate nitrate, and our mass-weighted total nitrate. So across all sites and forms of nitrate, we observe significant seasonality with higher values during winter and lower values during the summer that closely follows the trends observed in the mid-2000s, despite there being a significant reduction in NOx emissions, as well as a significant reduction in coal-related emissions. We also note that there is a significant consistent spatial difference in these delta 15N values for all forms of nitrate, in which our Abington site had higher values and the Woodstock site had the lowest values. So our subsequent analysis is to really determine whether this delta 15N spatial temporal variability tracks with NOx emission sources and or chemical influences. So in order to model our NOx emission sources, we first need to determine the source regions that contribute nitrate to our study sites. So we identified the source regions using air mass backdrifter calculations with the clustered results shown here. We then combine the backdrifter calculations with concentration data and use statistical methods to calculate the concentration weighted trajectories, which showcase that the majority of nitrate tended to derive within 1,000 kilometers of the CASPET sites. And then we manually created geospatial polygons to define the source region contributing nitrate to our various study sites. And we model the NOx emission regions within these source contributing regions using the community emissions data system, which is a high resolution emission inventory that is broken down by sector and fuel type. So the NOx emission results are shown here for both sector and fuel type. Overall, we find that there is a slight seasonal pattern with a maximum in the NOx emission density during the winter due to a significant heating demand for the study region. And then we also observe a peak during summer due to significant cooling demand. So when looking at the emissions sorted by fuel type, we see that liquid fuel dominates our NOx emissions across all sites. And then utilizing the NOx emission data, we then model the delta 15N values of our NOx sources, which is shown in blue. And we compared the modeled expectations with the monthly average delta 15N of the atmospheric nitrate, which is shown in red. So overall, we find that there is a significant large mismatch between the predicted and measured delta 15N values, as well as in the seasonality between these two components. The most likely explanation for this large discrepancy is that NOx emission sources are not the main driver in spatial temporal delta 15 nitrate variabilities. And we argue for that because the sources, if you look at our NOx compared to the nitrate, our NOx is much lower than our nitrate. If we were missing a source that had a high delta 15 value, this would really require more input from coal combustion, but that's not consistent with our fuel use data. So next we consider the role of NOx cycle fractionation on delta 15N. So in this cycle, NO is oxidized to NO2, which has an isotope effect of approximately -7 per mil. And NO2 is photolyzed back to NO, which has a near negligible isotope effect. Additionally, NO and NO2 may directly exchange 15N with a large isotope effect of 28 per mil. And as previously demonstrated, we can model the delta 15N of NO2 as the following, where delta 15N NO2 is equal to the delta 15N of NOx emission sources plus the isotope effect associated with NOx cycling and the amount of NO2 in the total NOx. So we have modeled the relative role of the different isotope effects associated with NOx cycle fractionation using geoschem output. And here I want to draw your attention to the bottom panel, the figure on the right, which showcases our modeled delta 15 NO2, which indicates that while there is this minor seasonality, overall the fractionation was really small typically less than 1 per mil. And I think we can conclude that for our study sites, the NOx cyclofractionation really played an insignificant role on fractionating delta 15N. So next, we considered the role of fractionation associated with nitrate formation. We have modeled the delta 15N of nitrate, assuming that is equal to the delta 15N of our calculated and modeled NO2 and the isotope effect associated with nitrate formation. So for the polluted mid-latitudes, nitrate formation is really dominated by 2 production pathways that include the homogeneous NO2 plus hydroxy radical reaction that has predicted isotope effect of about -3 per mil, and the N2O5 hydrolysis on aerosol surfaces with a predicted isotope effect near 28 per mil. We can then rearrange our first equation on the right and solve for this isotope effect and apply a simple mass balance calculation to estimate the relative role of nitrate formation from these 2 dominant pathways. Overall, from this calculation, we find our expected seasonality in nitrate formation with higher contributions from the NO2 plus hydroxy radical formation pathway during the summer, which is consistent with our expectations because hydroxy radical is a photochemically produced oxidant, and we have a higher fraction of N2O5 hydrolysis during winter, which also makes sense since N2O5 is thermally and photochemically liable. Overall, across all of our sites, we predict the NO2 plus hydroxy radical dominates nitrate formation with an average of about 63%, which is in pretty close agreement with our recent optimizations using oxygen isotopes of these same samples that we compared to geochem output. And this work was presented in a poster by my student Hee-Jung Kim last night. So overall, I think these calculations demonstrate that delta 15 of nitrate seasonality really tracks with nitrate formation. And this could be a really important tool for us to evaluate model nitrate chemistry to potentially improve our model mixing ratio and deposition expectations, which tend to be over predicted in the northeastern United States. So while the delta 15 in seasonality really seems like it's tracking with chemistry rather than sources, that is not to say that the delta 15N can't be useful for evaluating NOx emissions. So here I compared the delta 15N measurements at Connecticut Hill, New York, which was an overlapping study site in this work, as well as the work previously conducted by Elliott et al. From samples collected in the mid-2000s. For both nitric acid and particulate nitrate, we observed a long-term decrease in delta 15N, which likely reflects the decrease in coal combustion during this period. And thus, I think long-term evaluation of the delta 15N values at deposition sites, including NADP and CASNet sites, could be extremely useful for evaluating responses of emission reductions on deposition. And I think I would argue that establishing long-term records of isotope values at our deposition networks could be really useful for evaluating responses and emission reductions at a source level. So in conclusion, in this work, we've updated the delta 15 in values of nitrate from CASNet samples collected in the northeastern US. Overall, we find that the seasonal delta 15N signatures really seems to be tracking with nitrate formation rather than with NOx emission sources. We observe a long-term decrease in delta 15N, which likely reflects a decrease in coal combustion related NOx emission. And then using the community emissions data system, it appears that it's getting the relative proportion of NOx emissions correct in the northeastern US. Thank you.
Great. Thank you, Wendell, very much for a very interesting talk. We have time for one very quick question. Doug?
Oh, I think Emily Elliott at one time was kind of working with a hypothesis that there could be an increase in biogenic emissions in the warm weather season that could cause some of that seasonal variation? Is that something you can pretty safely rule out?
We consider the role of soil emissions, biogenic emissions. I think the problem with our NOx emission model compared to our observations is that we're already predicting lower than our observations in this model. And so if we had more biogenic emissions, it would even make our predictions even lower. So it would make the discrepancy even larger. So in the current work, at least for the northeastern US, we don't think biogenic emissions are necessarily underpredicted.
Great, thank you again, Wendell.
right,
We're going
thank
to
you.
have to move on to a couple of talks about dry deposition. We're going to start with Colleen Bablitz with the U.S. Environmental Protection Agency.
Great. Okay. Hi, everyone. My name is Colleen Boblitz. I'm a postdoc at the US EPA, working with John Walker, Jesse Bash, and with a former postdoc in John's group that's now at RTI, Jiang Wu. And I just want to quickly acknowledge these folks who have been excellent collaborators as well as mentors in my time at EPA. So thank you so much. Okay, so the project that I'll be presenting here, we're attempting to develop an inferential model for dry deposition that is applied across the US Ammonia Monitoring Network, or AMON. So there's been a lot of great information presented here about the role of ammonia in terms of air pollution, as well as ecosystem exposure and water quality degradation. And I'm just going to piggyback off of all of those great talks to jump right in to sort of what we're doing to try and get a better understanding of this process in particular. So the main loss pathway for atmospheric ammonia is through dry deposition, which models like STAGE represent as an electrical circuit. And so STAGE is currently a deposition option available in CMAQ, and it's part of the Equates time series project that's in development at the EPA right now. This deposition option can also be run offline, and so that's how we're applying it here. So here in this figure, I'm not going to, describe everything that's going on here, but just broadly to show you how deposition or dry deposition is represented. It's through this series of resistances for different pathways. So how resistant is that particular pathway to the uptake of ammonia? And just at sort of a high level, these pathways include to the soil, as well as, oh, that's unfortunate, as well as to plant leaves through their cuticles or stomata. And one last thing I want to mention about this process is that ammonia dry deposition, unlike other species we might think of that have large loss through deposition, like ozone, ammonia deposition is bidirectional, parameterized based on this compensation point. So ammonia can be re-emitted following its deposition. Excuse me. Okay, and so this process, although it is influential over atmospheric ammonia, is challenging to measure, such that there are a few long-term observations of this process. And so we're attempting to both get as close to available observations as possible and to develop more of a process-based understanding using this framework, which, again, we're starting out using the Ammonia Monitoring Network, or AMON. So I'm not going to step through everything that's on this slide, but just broadly to give you a sense for what goes into this framework. We have input parameters that are drawn from publicly available observation-based data sets for meteorology related to plants, as well as soil parameters. Importantly, we're using the CASNet and AMON data. Some subset of these, in particular the meteorological inputs, are also initially processed through the NOAA land surface model to collect friction velocity and soil moisture, so sort of some more specific meteorological parameters that are used as input by the STAGE model, which again we're running at the field scale in order to simulate ammonia net and component fluxes for each of the AMON sites. So one thing that is really exciting about this project is we have available pilot site observations for several of that are co-located with several of the AMON sites. I'm showing here just sort of some preliminary results we have through an initial evaluation of this framework at Bonneville, which is an agricultural site in Illinois. So on the left, I'm showing the aerodynamic conductance, and on the right, I'm showing the leaf quasi-laminar boundary layer conductance. The red shows our framework using STAGE, and the black shows the sonic anemometer measurements from this pilot site. So we can see, I think this shows, STAGE is doing a reasonably good job, both at representing the magnitude and variations of these sort of physical parameters in this process. So we still have quite a lot to do with this, and I'm looking forward in the future to additional evaluation against the other pilot site measurements, which are in natural systems, including Duke Forest in North Carolina, as well as Chiricahua, which is a more complex terrain grassland site in Arizona. Okay, and so broadly what we're hoping that this framework can offer us is a tool to answer the what, when, where, and why of ammonia dry deposition. So broadly, we can use this to attempt to describe, how ammonia dry deposition is varying seasonally and over the United States. We can pull it apart to ask, which processes are modulating ammonia dry deposition. And beyond that, we hope that this will give us some large-scale insight into where new observations might be most useful for constraining the model representation of this process. Okay, so first, I just sort of want to show at a high level, what this framework is suggesting is the spatial distribution of ammonia dry deposition over the United States. So here I'm showing the total simulated ammonia dry deposition across AMON sites for 2017. So as I mentioned earlier, ammonia dry deposition is bidirectional, and so negative values here represent a net sink for deposition, and positive values represent a net source. So, one thing we found interesting in approaching this is we see some broad spatial coherence in terms of the patterns this framework seems to suggest are represented through ammonia dry deposition. So in the eastern US, we see that there seems to be a net downward or depositional sink for ammonia, whereas out west, we're finding net upward or reemissive fluxes in the west, right? And so, with this framework, we can try and take a closer look and ask, why might that be the case? What's driving the patterns we're seeing here? Okay, so I'm going to step through a little bit more of like a process-based analysis in the next few slides. So returning to our overview schematic, I just want to remind you of the processes that are at play here, and also to just step through the specific input parameters that go into the calculation for the resistances for each of these pathways. And so, we use, again, the meteorological, plant, and soil input data to calculate these resistances. In the case of soil, we draw from soil pH, air temperature, and friction velocity. And for the plant leaf pathways, both the cuticular and stomatal pathways are dependent on air and soil temperature, as well as relative humidity. The cuticular pathway is additionally dependent on this empirically derived factor known as alpha cuticular that represents or that relates the cuticular resistance to relative humidity. The stomatal pathway is also dependent on shortwave radiation and friction velocity. Okay, and so one thing we find when we try to break the total annual fluxes into the component pathways is that it seems there are a few sites out west that dominate the overall signal when they're included, and so I've sort of highlighted them with boxes in the map that we saw a few slides ago on the lower right. So here I'm showing a breakdown of the soil, stomatal, and cuticular flux pathways as they contribute to the total annual budget across AMON. And so what we can see, with the red indicating a net upward flux and the blue indicating net downward, what we can see is that, the soil pathway dominates the overall flux budget. This is, and also that the net fluxes in this case are upward, which both of those were fairly surprising findings. And so if we exclude these high soil pH sites, we get something that I think looks a little bit more like we might anticipate, which is where the fluxes are net downward, and also that the cuticular budget dominates the overall signal. And so, we might ask ourselves, do we think that what this, framework is suggesting in terms of this very large influence of soil fluxes is realistic? And so we sort of conduct this somewhat crude mass balance approach, where we have used the National Trends Network wet deposition budgets for nitrogen at one of these high soil pH sites to try and see if we can recover on an annual basis essentially the extent of upward fluxes that our model is representing. And so that's sort of what I'm showing here. The black are measurements of nitrogen deposition from NCN, and the red are our framework for aim on stage. And so what we can see, I just want to call your attention to the difference in the y-axis on this plot. There's several orders of magnitude difference between, what is observed to be deposited through NCN versus what is represented as an upward flux. And so, this suggests to us that it's likely not realistic that these high soil pH sites have such large evasive fluxes. But that being said, we're using, what we believe to be like some of the best available representation of these processes. And it would be really nice to be able to have some more constraints on this process and the influence of soil pH, in particular in these high soil pH ecosystems out west. So beyond the influence of soil pH, we can go through each of the input parameters individually and try to assess their independent role on ammonia dry deposition. So we do that using a series of sensitivity simulations where we perturb these input parameters and compare them to the base case that I've been describing so far. Here I'm showing an example with shortwave radiation, which I hope is like a somewhat simple example. So essentially this is showing the diurnal profile of shortwave radiation, or essentially incoming sunlight at one site, Sand Mountain in Alabama. So the black line is showing the average diurnal profile for shortwave radiation at this site in winter. And the blue lines show essentially the envelope that we're using in our sensitivity simulations, which represents a standard plus or minus one standard deviation that's specific to that site, season, and hour of day. So this is our approach for the sensitivity simulations as relates to the meteorological input parameters to our model. Some other input parameters that we perturb to consider the influence are soil pH. We've modified this by plus or minus 0.5, which is like quite a lot in terms of the exponential scale that pH represents. But I'd be very open to hearing folks' thoughts if you have any suggestions for how we might better approach that. Something that I didn't have a chance to mention earlier is that we're using in our model hourly values for ammonia concentrations that are basically developed using the biweekly measured AMON ammonia scaled using the hourly equates simulations. So we essentially normalize it using what the model suggests is a diurnal profile for ammonia in that location. And finally, we also modified the empirical factor alpha cuticular that's been derived from a series of field studies that generally took place in Europe to see how much influence that might have on our overall understanding of ammonia dry deposition. Okay, so looking across these sensitivity simulations, we find, there are a few parameters that emerge as most influential over the annual dry deposition budget across AMON. So first, I just want to get you oriented to this plot. There's going to be a lot of stuff on it, but I'll try and step through it so it's a little bit more digestible. So I'm going to show daily average simulation values, and that's what's shown on the x-axis is day of year for 2017. The y-axis is the total flux, and so first I'll show here's our base case simulation. This is across all of the AMON sites. The alternate y-axis is going to show the difference from the base for each of the sensitivity simulations. And the specific input parameters that we perturb are going to be shown by different colors. So here I'm showing first soil temperature. We have hatching, in this case representing either the decreased or increased soil temperature cases. So here we can see, a larger influence, for example, from decreasing soil temperature than from increasing it, which could, have climate implications long term. Okay, and so here's the mess. But so I've already, taken off. We consider more variables than this, but I've just sort of included here, the three that we're finding so far are the most influential, which are soil pH, soil temperature, and this alpha cuticular empirical factor. I don't think it's necessarily shown so far as the most influential, but I also include our case where we just apply, instead of those hourly normalized values, we just directly use the biweekly AMON concentrations to see if that changes our results very much. It looks like it largely doesn't, except in periods where there's large day-to-day variability, as one might anticipate. And so, for example, we can see, in the springtime that there's a large negative incursion associated with that. That could be associated, for example, with fertilizer application at the start of the growing season, although we haven't, more conclusively looked into that. Okay, and so I think that this plot, because the base values can be negative, I think this plot can be like a little bit counterintuitive. So I just sort of want to step through that a positive difference between the base and the sensitivity could potentially indicate that the sensitivity is a stronger sink than in the base case, whereas a negative difference could indicate that the sensitivity flux is more evasive or there's greater re-emission of ammonia. Okay, and so we see, sort of as hinted at earlier in the presentation, that high soil pH seems to be the most influential factor in our analysis overall. So what that leads us to conclude in terms of the last question that I started off this presentation with is that, new observations might be especially useful if they were to target the soil pH and soil resistance relationship over the Western US in order to improve model representation of ammonia dry deposition. And so something that I didn't have a chance to talk about here is that these high soil pH sites that are very influential over our total model budget all happen to be grasslands as well. So I was very excited to see Jen's presentation earlier, having some nice measured constraints on grassland fluxes of nitrogen. Okay, and so also something that I'm looking forward to is data from an ongoing collaboration between the EPA and USDA in the Snake River Valley of Idaho. Okay, and so I have, just sort of a quick summary slide. And so here we've developed a new inferential modeling framework for field scale dry deposition across AMON broadly. This has influence for in particular, fine particle pollution, ecosystem nutrient exposure, as well as water degradation. We've identified that it could be that high soil pH western grasslands would be an especially useful place to have new constraints on our model representation of ammonia dry deposition. And overall, we hope that this framework may be useful in helping to characterize uncertainty and informing measurement strategies, as well as potentially offering an independent data set for comparison with the TDEP maps, or possibly incorporation into TDEP maps. We need to work more closely with Greg on that in the future. Okay, thank you so much.
we've got a minute or two for questions.
Hi, Colin. Great talk. My question is, have you considered kind of rich fens and alkaline lakes as also potential sources?
Okay. So we have sort of a large-scale representation of land cover and sort of sorry. Wait, I'm trying to go back to my. Sorry, and as far as our representation of the ecosystems that go into this, and so I have, some parameters that relate to like the MODIS like representation of land cover for one. We also have a somewhat coarse representation of the I'm sorry, I'm trying to recall of the stomatal compensation points that I'm not sure get to the level of specificity that you're describing. I think they're like a little bit more coarse than that. But I'd be very interested to chat with you more about this afterward if you feel that is something important that we should definitely include. Thank you. Mm-hmm.
Okay, we've got one more talk in this short session to wrap up the session, and then before we break for lunch, a man who needs no introduction, Bruce Hicks, now with MetCore and the University of Tennessee, is going to continue our discussion of dry deposition.
Well, it's always a pleasure to be in front of NADP. I hate to think the last time I was addressing this audience, but my mind has gone back to how we got into this dry deposition business in the first place. Now, my goal today is to actually leave you with a suggestion about how the program can step forward by calibrating existing sites. I have another goal too, and let me go into that immediately. The second goal is to make you leave here with a question in your mind about where the Schmidt number to the 2/3 power arises in the various models. Going back, that arose because Marv Wesley and I made up our minds that it was appropriate. I now believe that Marv and I made a mistake. It wasn't the first time. However, think about that, will you? Because to my mind, the result, which is so famous in chemical engineering, is solely due to it being based upon pipe flow, where you have flow in a confined space. However, that was the second point. Going to the first point, we now have a community that has a very, very productive research program going on, air surface exchange, not just dry deposition, but air surface exchange in every facet of the air chemical environment. And I endorse that. Fantastic. It's not that great different from what we had in mind when we started up dry deposition in NADP. I came in, Alice Cowling, a buddy of mine, and I had this vision that we needed to have dry deposition sites here. And NADP set up a committee to investigate how it would be done. I'm not going to read these things, you can read them. Okay, so NADP had a committee. It went out there and it looked at all the various ways in which other people around the world were looking at this issue. Canada cropped up as number one. Could we just simply adopt the CAPMON procedures? So we spent a year and looked at those devices that they were using, filter packs. And what we found was that the pressure drop involved in them and the humidities that we find in Tennessee, in particular and south of us, are such that you could expect that when you cracked one of those open, you might find liquid coming out. In other words, the filters were getting wet, and hence the suspicion was that sulfur was being reported as sulfate and not as gaseous SO2. So we said, we will not use that. We'll use something, we'll put a heater on the front end. We'll limit it to just 5 degrees Celsius, but that's enough to get past the diurnal humidity cycle in the southern United States. So we put that in place, and we started up a program looking at it, and we had that going ahead. Look, I was at that time involved in the National Acid Precipitation Assessment Program. We had several things going on in parallel. We had NADP wanting a dry deposition program. We had NAPAP endorsing what NADP wanted to do. We had Congress saying, hey guys, that's fantastic, phenomenal. And when NAPAP put it in its budget, lo and behold, Congress added money to the NAPAP budget. Congress decreed that the money be disseminated by EPA. In the corridor, Jackson Square in Washington, the head of the EPA at that time, who was instructed to handle this money, and I had a meeting. The question to me was very simple. Can you give us dry deposition measurements alongside what NADP is doing for wet deposition? I said, the science is not there, but we have a program to step forward. The response was, in that case, I will give the money to somebody who says he can do it. All else followed. That's the reason you haven't seen me at too many of these meetings. I got thoroughly and absolutely pissed off. But we went ahead with what the NADP was suggesting anyway, on a wing and a prayer. And we made this program, which had sites at different levels of complexity in different places, and we stepped ahead with that for many years, and we made some breakthroughs, yes. We got measurements of sulfur, where we didn't think we could in the past. We went on to the NOx, and finally to NOy. And we developed the multi-layer model. That was developed as a part of the NADP program in its early days. By early days, these are not early days for me. I'm talking about 1980s. That's not early. I have learnt that the way to handle, the way to get success in the scientific environment is to outlive your critics. This is what we have, or my depiction of it. I don't want to pay attention to the details of this. I'm just throwing up the fact that we have a hell of a lot of sites where good measurements are being made. This is great, fantastic. But I'm now promoting that we could go out there to a select number of these and actually calibrate them. Look at this. I'm changing eddy correlation. I'm saying that if you have a sensor that is operating so poorly that you don't trust it for standard eddy correlation, instead of relying on it absolutely, accept the fact that the transfer of that trace gas or chemical species is going to be governed by the transfer of heat. So measuring the flux of heat is damn simple. Go out and do it. But as you're doing that, take that temperature signal you're using, plug that into where in that data recorder it says, I'm going to compute a covariance, And then also plug in that output from the lousy covariance sensor, that lousy chemical sensor. All right? So here, in red, we have the temperature data going in. In blue, we have what your sonic anemometer, I presume a sonic anemometer, doesn't have to be. And then independently you get that lousy C data. So come up with 3 different covariances, 3 different correlation coefficients. I'm expressing this in terms of the correlation coefficient because I believe in eddy correlation. You speak about covariance and what the hell, it doesn't matter. But the mathematics, and the story I want to leave you with, is that as I promote this, I don't know of anybody in the world who's ever done it. I'm promoting it, I'm throwing out at you guys. If you get the opportunity, test this out, because if it is right, then we have a method, because we can come up with the eddy flux that you're interested in. Very simply, as expressed there. Bear in mind there's an assumption. The assumption is that the correlation coefficient between your chemical and temperature is close to 1. Now, in all that's holy, that falls in the category of we hold these truths. It ought to approach that. Of course, it probably doesn't. And the question is, I don't have the answer is that I don't have data to test that out. People sitting in this room have data. So I'm throwing this up there in the hope that some of you will go away and say, look at what that lay-visiting idiot was telling us. And look at this. He was absolutely wrong. Well, could be. However, if we test it out and it proves that I'm not wrong, we have a method now to make lousy sensors useful. So what are these new sensors? Here's a variety of them. Some of them are solid state. There's a big unfortunate thing about the solid state sensors available today. Inevitably, they're made in China. Doesn't worry me, but I can see that maybe the availability might suffer in the near future. So, my claim, the technology is now here. New instruments are available. I think it's now possible to calibrate NADP sites, some of them, not all of them. By the way, I'm hyper aware of the fact that there's an ongoing dry deposition program here that is relying on using models to come up with these same data. I claim that their outputs are what the model tells us. I want to go out there and test the sites and see whether or not we can get absolute reference points. At that, I'll take you back to where I came in. Please think about the Schmidt number to the 2/3 power and think it through. I have not published this. Well, actually, it will be published early next year. I have a book coming out. It'll be in there. So anyway, thank you for this opportunity. You folk are doing fantastic work. Keep it up. And this, I think, is something that's worth testing. Thank you. And by the way, all of that initial work was done under NAPAP, and it's all described in the NAPAP Science and Technology documentation. If you don't have that documentation, I have 5 copies of it right here. Come and grab, they'll go fast.
Any questions Or someone willing to stand up and take that challenge? Anyone?
Lunchtime.
Could be. Anything online? Nothing online.